Okay, the next contract that I'm going to show you is going to step up the complexity yet another order of magnitude. And we are going to build a simple coin flip contract where two people can send Ether to a smart contract. The contract will flip a coin to randomly determine who wins the coin flip and automatically send the Ether to that person. And this is going to be inching closer towards an actual smart contract that you might see in production. Now, before we look at the code, I just want to touch on one of the core concepts that I'm going to need for this contract, called a finite state machine. A finite state machine is a general programming concept for modeling stateful domain objects. And the idea is that an instance of an object can exist in exactly one of a finite number of states at any given time. And there are three important things to determine when modeling a finite state machine. First, what are these discrete states that your instance can exist in? Two, what events are exposed in each state? Because you might have specific events that can only be called when the instance is in specific states. And only some of these events will actually trigger a state transition to a new state. So you need to determine what those are. And third, what artifacts are going to be produced on transitions between states? So that might be a little abstract. So let's look at a real example of this that you might see out in the world, which is an order in an e-commerce system, which is often modeled as a finite state machine. In this example, an order can exist in one of 6 different states at any given time: in cart, purchased, confirmed, shipped, received, or completed. The order will start in cart when the user adds it to their cart and creates it. And that will expose an event called purchase, which requires the user to fill in their credit card information and hit submit. That will send something to the payment gateway, which will either accept or decline the credit card. If it accepts it, that will transition the order from in cart into purchased. And on that transition, that might create an artifact such as a receipt that you want to email to the user. So that's a good example of an artifact being created on a state transition. So we transition states, that sends an email to the user with their receipt. Now you might have some admin tool that requires the admin of the site to make sure that the order isn't fraud and manually confirm it, which will send something to the fulfillment provider saying that you can go ahead and ship this order. So that will live in their system until they ship the order and transition the order to shipped. And at any given time, somebody could just query the order and say, what state are you in? That's the idea, that you could just ask at any time, what state are you in? So we could see that this is in the shipped state, which means we know that it's waiting to be received. Once it is received, it transitions to the received state. And then maybe you have an automatic process because maybe you can refund an order for up to 30 days, but after 30 days is done, there's an automatic process that will then transition the order from received to completed. Now, a lot of different smart contracts are going to function as finite state machines. Our coin flipper contract is going to have 3 separate states. No wager, which is the initial state that the contract will be in when it is created. And this will expose a method called make wager, which player 1 will call by sending ether to, and that will transition the contract into wager made, where we have some amount of ether that is now the wager. And that will expose a function called accept wager, which player 2 can send that same amount of ether to, which will transition the contract to wager accepted. And that will expose a function called resolve bet, where now somebody can call to resolve the bet that will randomly determine who wins. It will send the ether to the winner and then transition the contract back to no wager. So let's look at how we could model a finite state machine in Solidity code and actually deploy that contract. So before we open Solidity, I just want to add a couple quick helper functions to our node console so that we don't need to keep doing repetitive stuff every time we want to deploy and query smart contracts. So up until now, we've been opening our node console by just running the node command, but you'll notice that we don't have anything by default, like we don't have access to the global web3 variable. So here's a quick little trick. I'm just going to open a new file called temp.js, and I'm just going to write require REPL.start and then pass an empty object into that and save. So now if I run node temp.js, you'll notice that this runs a node REPL just like anything else. But this now gives us the ability to add scripts before the REPL process actually starts so that we have pre-configured variables in a REPL. For example, I could do global, which is the global namespace of the REPL, .web3 equals require web3 save this, and then start the REPL with node temp.js, and then I'll have access to the Web3 object by default whenever I start up the REPL. So I've pre-written a bunch of helper functions which I put in the namespace decipher.js. And just really quickly what this does, it will require the Solidity namespace, the Node.js file system namespace, the Web3 object, and then it will create a new instance of Web3, put it into the global namespace as defined in this little config object up here. It'll make a couple quick accessor functions for each account so that I can just do account 1, account 2, account 3 to reference accounts instead of this long stuff. And then I want to draw your attention to this function right here, which will actually take the name of a Solidity file, and then it will compile that code, it will create a new contract instance, and then it will deploy that contract to the actual test RPC so that we have a one-liner for just deploying a contract. And then there's this one helper function called ether balance, which will just be able to quickly get the balance in ether of either a contract or an account. And then that loads this into the decipher namespace on the global object and then starts the REPL. And don't worry about copying this because this exact file is in the video notes at the top of the page. But just to show you, for example, what that does, I will start the test RPC down here. And then I can start my console by doing node decipher.js. And that will preload a bunch of data. So that will, for example, I can run account 1, which will just be the first account. I could do decipher.ether balance account 1 just to check the balance in ether of that account. And I have one-liners for deploying contracts. So this is the new dev environment that we're going to use going forward. So I'm going to make a new file called flipper.sol. And I'm going to make a new contract called Flipper. And the first thing that I'm going to do is declare a new data type called GameState. And I am not declaring a variable here. I'm actually declaring a new data type that is going to be an enumerable value. So an enumerable value, also called enum in most programming languages, is just a fixed set of values that a variable can have. So this is perfect for representing a finite state machine where we can just declare a data type called GameState that can only be specific values. So I'm going to say that it can be the value no wager, wager made, and wager accepted. And then any other value that a variable of type GameState has will be invalid. So then I can declare a variable called current state of type GameState. So just to make this clear, we define a data type called GameState that can only have these three values, and then we're declaring a new variable called current state that is of type GameState. And I'm just going to make this variable public so that we can query it from our console. Next, I'm going to create a constructor function, and this is just going to initialize the state. So it's going to set current state equal to GameState.noWager. And this is how you reference the value of an enumerable, is you just say GameState.noWager and set that equal to current state, and that's a valid value for this variable. Next, I'm going to create a function called transition GameState. And this is just going to be a function that takes a string as an argument, and the string will just be a valid state, and we will just transition to that state. Now, just a note about Solidity. When you want to write a function that takes a string as an argument, for some reason, you do not declare it as data type string. You declare it as data type bytes 32. So I'm going to have a variable called target state that I pass into this function of type bytes 32. Why this is the case has something to do with the EVM, and I will talk about it in a later video when we go into the EVM in depth. But for now, it's just one of those unconscionable developer experience things that are really frustrating to deal with, but you just need to take it on the chin and just roll with the punches. And just know that if you want to take a string as an argument, you declare it as type bytes 32, but you can use it as a string the way you would normally represent a string inside the function. And we're just going to have this return a Boolean value of true or false and whether or not we actually transition the state. So I'm going to say if target state equals no wager, then we're going to set the current state equal to GameState.noWager, and I will just return true. And this is an example of a state transition. So if this is the argument, we transition state to no wager and return true. And then I can do else if target state is equal to wager made, Then we will transition to that state, game state dot wager made, and we will return true. And else, if the target state is equal to wager accepted, then we will transition to that state, game state dot wager accepted, and return true. And if the argument that we pass in is not one of these three states, we will just return false from the function. So let's stop that right there. I'll leave that console open. And we should be able to use our one-line deploy script to just go ahead and deploy this function. So I'm going to set var deployed equal to decipher.deploy contract, and then pass in the string flipper, which needs to be the name of the file that we want to deploy, and it looks like it did deploy. So we should have access to this deployed object. Then we should be able to check an address, and it looks like this is deployed onto the Ethereum blockchain. Now, because current state is a public variable, I should be able to do deployed.currentState.call to get the current value. And you'll see that the enumerable value is represented as an integer representing the index in this data set that the variable is. So this gives us 0 as a value, and that's because it is the 0 index in the game state. So in order to test that this is working, we can call deployed.transitionGameState. And I'm going to pass in wager made to transition the game state. And just a note, you're going to need to pass in the account that's calling this function because they need to pay the gas cost to actually call into the contract. So I'm just going to do this from account 1. And that looks like it did actually make a contract call. And now if I look at the current state, we'll see that the actual current state has transitioned to state 1, which is state wager made. Now if I passed in something nonsensical like XYZ, something like that, which is not a valid game state, I can now do deploy.currentState.call, and it's still in state 1. And if I try to transition game state to the final state, which is wager accepted, and then currentState.call, we'll see that it's now in state 2. So this little function to manually transition the game state looks like it's working correctly. Okay, so I'm going to blow away this transition game state function that we've been using and replace it with the templates for the actual functions that we are going to use in this contract. We're going to have a function called makeWager that's going to do something, transition the state to wager made, and then return true. We're going to have a function called acceptWager that's going to do something, then transition the state to wager accepted and return true. And then we're going to have a function called resolveBet that's going to do something and then transition the state to no wager and return true. Now, it would be great if we could somehow validate that the game is in the correct state before actually calling out to these functions so that we're not calling resolveBet before a wager had been made, for example. And there's a great way that we can do this using something in Solidity called a modifier. A modifier is a way to make reusable code that you can put into function definitions that can ensure some sort of data is valid before even proceeding with the function. Let me show you how you do this, and then I'll explain why it's useful. So we can define a modifier by just using the word modifier. In this case, I'm going to create a modifier called onlyState. And onlyState is going to take one variable called expectedState, and this is going to be of type gameState. Now this is going to run some code block, and in this code block I'm going to run a conditional statement that says if the expected state that's passed into this modifier is equal to the current state of the contract, then underscore semicolon. Now, what underscore semicolon means is that you just want to delegate out to the function that defines this that uses this modifier. So you can think of underscore semicolon as just replace this with the actual definition of the function. So if one of these functions says I want to use this modifier, it will automatically check if the expected state that's passed into this modifier is actually equal to the current state of the contract. And if it is, then it will execute the function. Or else, we're going to do something that we have not seen yet, which is throw an exception. Now, throwing an exception behaves slightly differently in Solidity than it might in other programming languages. And the reason is because Solidity does not have a full exception handling environment and model the way that other programming languages would, for reasons that have to do with the complexity of the distributed Ethereum virtual machine. Now, An important thing to know about making transactions in Ethereum is that all state transitions from a transaction are what's called atomic, which means if you modify, say, 8 pieces of state in a contract from a single transaction, either those modifications will be mined into the blockchain and all 8 state transitions will happen, or they will not be mined into the blockchain and none of the state transitions will happen. There's no way to have a partial update where you modify 8 pieces of state, but only 4 of them go through, but 4 of them don't. That's never going to happen. It's an atomic operation that either all succeeds together or all fails together. Now, the thing that will define whether or not a transaction goes through is whether or not enough gas is provided to the transaction. So if you provide not enough gas to a transaction, only enough to modify half the state that you want to, the entire transaction will get rolled back and none of it will get mined in the blockchain. So throw is essentially a hack in Ethereum that just drains the transaction of all of its gas so that none of the state transitions are actually valid and the entire thing is like it never happened. So in this case, in the modifier that we're adding, if the state of the contract is not in the correct state that we need to execute the function, everything will just get rolled back and nothing will happen, which is actually the behavior that we want. So the way that we can introduce the modifier into the function is just by defining it on the function definition. So in this make wager function, I can say only in state game state dot no wager do I want for this function to be able to be called, or else it's going to throw an exception. And likewise, for accept wager, we can say only in state game state dot wager made. And for resolve bet, we can only call this if the contract is in state game state dot wager accepted. And let's deploy this contract just to see what this looks like. So I should be able to just go back to wherever the code is to deploy this and just hit it again to redeploy with our one-liner. And I should be able to check the deploy.currentState.call and see that it's in state 0, which is no wager, which is correct. Now I should now be able to call make wager. So I should, because it's in the right state, so I should be able to do deploy.makeWager. We'll just do from account 1. And it looks like that went through and transitioned our state, so that now we're in state 1. Now, I should not be able to call resolve bet because the wager has not been accepted. So let's see what happens if I try to call it. So let's not call make wager, let's call resolve bet, which should be an invalid transaction. And lo and behold, our transaction blows up. And we get this error that says VM exception while processing the transaction, invalid jump. Now, your console output might look slightly different than this, but you should still see this invalid jump. This is what is coming back from that thrown exception, which means none of the content of this function even got executed. We just errored out immediately. So if I looked at the actual state, we should still be in state 1, which is exactly what we wanted. And that is going to be useful for a lot of different functionality that we want to implement. Now, this is just the template for the functions. In the next video, we're going to actually implement the behavior of these functions, including how to implement pseudo-randomness on the blockchain so that we can actually resolve a coin flip bet.